everybody. Today we're going to talk about the effects of harmonics on an electrical system and some of the things that we can do to probably counteract the effects of harmonics within a system. So stay tuned for today's show. You're listening to Electrician Live with your host, Paul Abernathy. Well, hey, everybody. Welcome to the show, and hopefully you're excited about what we're going to talk about today, because we're going to talk a little bit about harmonics. We're not going to get too awful complicated because it is a podcast, but we're going to talk a little bit about it, how it can affect a system, and answer some of those questions people have about neutrals and why, when we have a 4-wire 3-phase Y system, the neutral has to be counted as a current carrying conductor, and all of those things that seem to confuse people. But yet you don't count the neutral in a single phase application where it only carries the unbalanced load between phase A and phase B. So we're going to talk a little bit about that today in this episode to kind of clear the air of dealing with harmonics. Now, if you're dealing with single family dwellings, residentials, you probably don't have any reason to worry about harmonics, okay? It's nothing that you've considered. There's probably something you don't need to worry about considering. It's not a big deal. Now, when you're dealing with commercial applications and most notably 3-phase systems, it is something that you have to take into consideration. But residential, usually not so much. But it's good that you have a healthy understanding of what harmonics are and what causes it in the applications. So that's what we're going to talk about today is harmonics and the problems that can be caused in many industries by harmonics. Now, what are some of the problems that can happen with harmonics? Now, they can range anywhere from overheating conductors, and we'll kind of talk about that in a minute when we talk about 4-wire, 3-phase, Y type of transformer setups and the conductors that come from the secondary. But yes, transformers in itself, sometimes harmonics, which is an elevated frequency, actually it's the multiples of the fundamental power frequency, and we'll talk about that in a second, but it can cause breakers to trip when they're nowhere near the capacity of the breaker. And so it can kind of throw people for a loop, especially if they have a transformer set up and they keep tripping a breaker and they keep going, what the heck's going on? I mean, I'm not even loading this transformer up and I'm tripping breakers at the secondary where those conductors from the secondary conductors terminate into an overcurrent device. Sometimes things trip and they're like, what in the heck is going on? And it really depends on the situation. Motors can burn out for no apparent reason prematurely. I'm a big believer in things like voltage drop, even though the code doesn't mandate voltage drop for normal applications. Do for fire pumps and emergency, but not under normal rules. The energy code mandates voltage drop applications, but the NEC really doesn't mandate it, just makes a recommendation. But I'm also a believer if you don't supply the right voltage to equipment, that will also burn up equipment. And that becomes a hazard, even though people say that the reason it's not in the NEC is because it's a minimum safety standard. But I would argue that voltage drop can be a safety issue. Again, not the topic of today. We're talking harmonics, but all of these things can exacerbate issues of harmonics. And so we want to understand the conditions that kind of can cause harmonics and how we possibly could maybe correct some harmonic issues if you're dealing with that. And so that's the topic of the day. We're going to kind of deal into that. Now, we're going to give you the 30,000-foot view here because it is a podcast. But there's a lot more on this topic that you could most certainly dig into and learn about harmonics. Now, the fundamental concept of harmonics, what are they? Harmonics are voltages and currents that operate at a frequency that is a multiple of the fundamental power frequency. Now, what does that mean? Now, typically, our power frequency is 60 hertz. So if somebody said that I had, and I hooked a meter on it or whatnot, and we measured it, and it said that we were at the second harmonic, then basically the hertz would be at 120 hertz, which is the fundamental power of 60 hertz to the second fundamental, which is 60 and 60 is 120. The same thing could be said if you're at the third harmonic. So it'd be 60, 60, 60. So that's 180, and so on down the line. So what are we dealing? How do we produce these harmonics? What makes harmonics? Because we know that the current sinusoidal waveform of a 60 hertz is nice and smooth, and we utilize it to cancel out one phase over another. If everything's sinusoidal, everything's going good. I have 10 amps on phase A, 10 amps on phase B. The neutral is going to carry 0. All this sounds wonderful in the concepts of electricity, except when you start getting into harmonics. Now, harmonics are produced by nonlinear loads. The difference is a nonlinear load is basically a load that's not constant. It's continuous. But what happens with a nonlinear, it is current that actually pulsates. Now that might be from switching devices, variable frequency drives, anything, triac light dimmers, the ballasts on fluorescent lighting, electronic ballasts that is, that actually are taking the waveform and they're breaking it down into a pulse. And many times when you're going from an AC and you're converting it over into DC, it has to take that AC and break it down into pulses. And once it does that, it changes a pretty uniform sinusoidal waveform down to a choppier waveform. And the problem is when you have high levels of harmonics or distortion in the system, it takes that fundamental frequency waveform and totally trashes it. Another example is we like things that are flowing. So if I had a lake, no, a lake's too big. Let's say I had a pond and I had a concrete wall all around it. I drop a boulder in the middle, it creates the waves that go out, nice ripply waves, symmetrical, and they travel across the top of the water. They hit the wall, and then they reverberate against themselves, and it literally takes this nice smooth waveform and literally chops it up because you have two competing waveforms. Well, if you think about harmonics, it's basically the fundamental of the frequency that actually is breaking down or distorting that nice sinusoidal waveform. In three-phase harmonics, for example, and probably what you're going to run into the most in three-phase applications, is you're going to run into things like variable frequency drives that do that, AC motors and electronic drives for DC motors. All of that's going to take the waveform and really distort it down and create a pulsing load. And when it converts AC into DC, then it regulates the DC voltage by what's called a pulse width modulation. At that point, it really starts to break down the waveform. And it can create the side effect of that is harmonics, which is a multiple of the fundamental power frequency. Again, so you could take a 60 hertz and all of a sudden you're dealing with 120 hertz, or it's a third harmonic, it's 180. And it kind of goes like that, okay? So, yes, you have harmonics in single-phase power lines. You have harmonics in three-phase power lines. Now, the fundamental difference in the single-phase is you're probably not going to deal with that, or you're going to even get remotely involved in that with a single-phase for residential. That's not the case. However, commercial, where you have three-phase into a building and it derives single-phase from that three-phase, then you still got the presence and potential issue of harmonic conditions that you have to be aware of. A lot of buildings, office buildings, have a lot of fluorescent lighting, a lot of computers that are basically changing the AC to DC concept, and it's really breaking the waveform down, and it causes all types of harmonics. Now, harmonics, again, are a problem because the characteristics of those harmonics can have negative effects on the electrical system, okay? So that's what we're going to get. So that's kind of the 3,000, 30,000, whatever foot view is. It's basically harmonics distort the current and voltage waveform, and they flow back onto other parts of the power system that causes unnecessary reactive conditions into the system, okay? So think of it that way. Again, think of a nice sinusoidal waveform, and now when you go to the second harmonic, the third harmonic, the fourth harmonic, it just puts more waveforms in a tighter space, and it starts to make it harder for the signal to cancel out, and there can be other issues that take place. Okay, that's just our basic. Let's keep. I'm trying to keep it basic as I can right now so we can build on this. Now, we've got to kind of look at what problems do we have, because I get a lot of calls from people where they have neutrals that are burnt out in their a 4-wire 3-phase Y system, and they run into a situation and they've got neutrals that are browned out or burnt up, and they don't understand what's going on. Their phase conductors aren't overloaded, breakers aren't tripping, but they got some issues. So some of the detrimental effects that harmonics can have, and hopefully engineers think about this when they're designing a system, not so much the electrician, they're just installing it. but there really is something that the engineers have to design, and total harmonic distortion and things like that have to be taken into consideration. But some of the effects that harmonics, if they're not taken into consideration, can cause symptoms that are overheated conductors, melting down or breaking down of insulation, plasticizer, migration out of thermoplastic products and things like that. Transformers that are overheating and constantly breaking down the dielectric separation, the resin between the primary to secondary. Things like that start breaking down. Again, circuit breakers that literally trip for no reason. Very common to have a transformer and have a secondary that terminates into overcurrent device, and that overcurrent device constantly trips. Yet you know you're doing a load calculation and you're not exceeding the rating of the output of that transformer, and you're wondering what in the world is causing these breakers to trip. Okay, so one other thing to realize is that harmonics are classified by their actual name and frequency. So we have what's called, there's a name, frequency, and sequence. So the typical fundamental of 60 hertz frequency that we use every day is what we call a positive sequence harmonic, and it produces a magnetic field and it rotates in the same direction of the fundamental frequency. So everything's going good. It's considered a positive frequency. It's 60 hertz. So that's the positive. Now, what happens is you get into the second harmonic, which is 120 volt frequency. Then you start getting to a concept where we have a negative sequence harmonic. And it kind of goes to that where you get to the third harmonic, and it is what's called a zero sequence. And we'll talk about those in a second, the zero sequence. So it kind of goes to positive, then negative, zero sequence. Then the fourth harmonic is 240 hertz, and that's a positive, and then the fifth is a negative at 300 hertz, and then six, it goes on its way all the way through the system. Okay, now when we talk harmonics, the most common one that engineers will refer to is the ones that they have to steer away from is what we call triplets, and they are the odd multiples of the third harmonic. So that's the third, the ninth, the 15th, the 21st, etc. Those are the more problematic ones that we tend to have to try to guard against. Okay. Now, harmonics with the positive sequence generally can cause overheating of conductors, transformers, and circuit breakers. Okay. Now, the negative sequence harmonics can cause the same heating problems as the positive harmonics, plus additional problems with various types of motors. And why is this? Because the phase or rotation of a negative harmonic is opposite of that of the fundamental frequency. In other words, the fundamental frequency goes one direction, and again, as we said, the negative harmonic tries to oppose that in the opposite direction. And this will tend to weaken the rotating magnetic field of an induction motor, causing it to produce less torque, thus will cause it to also overheat prematurely. Okay, so those are the kind of things. If it's not producing within its wheelhouse, its speed, its optimum performance, kind of like lack of voltage to a piece of equipment can cause it to not operate at its optimum rating. And all those things can cause motors to overheat and be very inefficient. Okay, all those type of things. Now, we really don't want to we really want it to be at our positive sequence, our 60 hertz. We don't really want any harmonics, okay? We certainly don't want to have the second, third, fourth, fifth harmonic, sixth harmonic. We definitely don't want to have what we call the triplet harmonics. Now, even though triplet harmonics, okay, have no phasor rotation, there is zero, okay? They still can cause a great deal of trouble in three-phase four-wire systems such as 208-120 or 480-277 system. So that's kind of what we're going to talk about now, because that's the biggest question I get from people is when you see whether or not the neutral current is considered a current carrying conductor, and we see this statement in the National Electrical Code that says, okay, you're going to treat the neutral as a current carrying conductor when you're dealing with a three-phase four-wire system. Example would be a 208-120 or 480-277 system that are a four-wire three-phase. And there's a reason why we generally have this issue. Now, this layout is very common and when we get transformers. It typically, in these three-phase four-wire 208 120s or 480 277s, is the primary is a delta, and it's the secondary that's the Y. And so that's the part that's going to be supplying the structure on the secondary side of this transformer. And if it is a 4-wire 3-phase, then it's things that we have to take into consideration. Now, single phase loads that operate at 120 volts are connected between any phase conductor and the neutral conductor. Okay, so the concept of neutral is any phase between the neutral or the grounded point and that phase is going to be 120 volts. So thus it's considered neutral, right? And we're talking the secondary winding, the Y, delta primary, secondary winding. So typically phase, A, B, and C, and between any one of those phases to the neutral, okay, would be a neutral conductor, okay? We're all square on that. Now the neutral conductor or the neutral current is a vector sum of the phase currents. Okay, remembering that in a balanced 3-phase circuit, all phasing have the equal current. So let's assume they're all the same. Then, of course, we've learned through the years that the neutral current is going to be 0. It's carrying the imbalance. Well, if there's 10 amps on A, 10 amps on B, 10 amps on C, then we're going to have 0 on the neutral. We're all familiar with that. We've done that through years. Now, although the single-phase loads tend to cause an unbalanced condition, the vector sum of the currents causing the neutral conductor to carry less current than any other phase current. Okay, that's why we don't have to worry about the neutral in that scenario. Okay, single-phase applications. Now, that is true for loads that are linear. Okay, that draw a continuous sine wave current like motors, things like that. That's a linear load. Okay. Other types of loads that simply are not pulsing nonlinear currents are simply, they're pulling the load. When it's on, it's pulling the load, and it is what it is. Now, when we're dealing with pulsating nonlinear, and that's when you start seeing in the code when it says that when you're dealing with a 4-wire 3-phase system that has a majority portion of nonlinear loads, for example, then you start understanding we're dealing with pulsating nonlinear currents that are connected to a 3-phase 4-wire system. Now, you throw triple harmonic frequencies, they disrupt the normal phasor relationship between phase A, phase B, and phase C, and the currents. And what this causes is the phase currents to add to the neutral conductor instead of canceling out. So it doesn't cancel anything out. Because of this concept with these harmonics, the waveform doesn't cancel out the same way. And so instead of canceling out phase A to phase B to phase C, they now don't fully cancel out. And so the unbalanced portion of this inability to cancel out has to be carried on the neutral conductor. Okay? And that's when the neutral conductor becomes an issue. Okay? So those triple harmonic frequencies will disrupt the normal phasor relationship of the phase currents and cause the phase currents to add to the neutral conductor instead of canceling. Why? Because the neutral conductor is not protected by any fuse or circuit breaker. You don't put fuses, you don't put circuit breakers, the code tells us, in the grounded neutral conductor. Okay? So what happens is, because this current, because of the triplet harmonics that are happening, starts to pump current onto this neutral, and this neutral does not have the same protection as the phasor conductors or the phase conductors. Okay, that becomes a problem, and that's why you have the neutrals that will brown out or break down prematurely. This is also why you see people buy cable assemblies, or they'll run an oversized neutral or a double-sized neutral or 200% neutral, because they know that they're dealing with this type of system that's going to put excessive amounts of current on the neutral conductor. Okay, so that's important to remember when dealing with a 3-phase 4-wire system if you have triplet harmonics. Okay, because the triplets can be worse in this situation. Now, the first thing that people ask me is this means that you only have a concern on the Y side. That's not true, because when you have these harmonics, the harmonic currents are also reflected over to the delta primary windings. And it can cause that winding to overheat as well. Okay? So the other thing is the heating problems are caused within the transformer is the eddy currents, and then you have what's called hysteresis losses in transformers, which is essentially a waste of heat It's not producing any real energy. It's just a waste. And so typically transformers are designed to operate at 60 hertz operation. So what happens is the higher their harmonic frequencies, they create more core losses within the transformer, and they can't handle it. And because they can't handle it, they start to break down, and it starts to break down the internal components, the separation medium, the resin medium between the primary and secondary and the windings, and all of that becomes a problem. Now, how do we solve this when it comes to a transformer? Now, most people, I would assume, know this, but you can actually buy a transformer that is designed specifically to operate within these harmonic frequencies. It's designed to operate within the third triplet harmonic, and you can get it, typically referred to as a K factor type of transformer that's designed specifically for this function or this condition. Now you're asking, how do I know I have this condition? Well, if you have a building that has this situation, it has a lot of nonlinear loads in there, a lot of fluorescent electronic ballast, a lot of computer systems, a lot of variable frequency drives, anything that can modulate the waveform and change it and pulse it, and a lot of stopping and starting switching, a lot of dimmer systems, all these type of things, you're going to have harmonics. And usually today they have systems that can actually monitor the system and tell you to what level their harmonics are at, okay? So that's just something to think about, but that is a solution for it. So one other solution, again, was the oversized neutral. But the other solution is, why not get a transformer that's designed to deal with this harmonic situation? Now, one of the other things that I guess people really don't think about is transformers is one issue, and why you'd want to solve the issue with the transformer. But also, when you have a lot of harmonic issues, it can also affect other things. Like anytime that you distort that waveform in some way, raising the frequency and changing things, you also can affect things like emergency systems or even standby generators and how they function. Some of these generators are very sophisticated, and whether they create what's called a dirty signal or not, or how they function, and the switching components between the standby emergency can be affected by these harmonics. So you need to be aware of that. Also, any type of data processing equipment can be extremely sensitive to harmonics. And you start wondering why data processing systems, IT systems start to really have problems. It can also be that you have an elevated harmonic condition that you're going to have to address. Okay, and some of the harmonic frequencies will get distorted as it crosses over the zero waveform line for generators, for example, and it creates a generator that is not producing an adequate frequency for the actual equipment that it's powering, and it's bad for the generator, it's bad for the system, it ultimately causes a problem. All right. Now, as far as breakers, we still have what's called thermomagnetic circuit breakers, and they utilize a little component in there called the bimetal strip. And it's a mechanism that's very sensitive to heat. So it bends upon heat to a certain point that causes the breaker mechanism to trip. All right. And it's designed to operate and respond to the heating effects of true RMS type of current values, not values that are generated by elevated, that would get too great due to harmonic problems. Okay. So harmonic currents cause a distortion of the actual RMS value, which is what the breakers or circuit breakers are designed on, which causes that breaker to trip when it should not. Okay, so thermomagnetic circuit breakers are generally better protection against harmonic currents than electronic circuit breakers for obvious reasons, because electronic circuit breakers sense peak value of current, and the peak harmonic currents are generally higher than the fundamental sine wave, so they can affect the electronic circuit breakers. So you have a little better chance of reliability with a thermomagnetic circuit breaker. However, if again the harmonics are high and it's pushing that true RMS to a higher level and the heat starts building up because of these harmonics, then you're going to have false tripping in a circuit breaker as well. So that could be one of the things to think about. Now, we got to I guess we need to circle back to the neutral. So dealing with triplet harmonics, and we talked about earlier the triplets, that's the odd multiples of the third harmonic, like the third, the ninth, the 15th, the 21st. Most of the time you're going to deal with the third, but harmonics can really cause problems on neutral buses, neutral terminals, neutral lugs, because the neutral bus is designed to carry the rated phase current. But because triplet harmonics can cause the neutral current to be actually get higher than the phase current because it's taking the offcast of all the phases, that it's possible that the neutral can become overloaded. And so, again, it has no overcurrent protection on it, and so that becomes a problem, and that's a quick source of breaking down. Now, electrical panels and bus ducts are designed to carry currents that operate at 60 hertz. Okay, so when we're dealing with harmonic, which is obviously going to be a negative thing, the harmonic currents are going to produce a magnetic field that operates at a higher frequency. So again, it's operating at a higher frequency than some of this equipment was designed to operate at, and that becomes a problem. Now, one of the things that you can tell is that the panel or bus panels can vibrate due to this frequency. Everything's based on frequency, sound, vibration, everything. So it produces a buzzing sound in the harmonics. That sound that you will hear can be a situation inside of an enclosure where the harmonics are so bad that it's literally causing a vibration to take place inside of the equipment. Okay. Now, some of the other side effects that people deal with is, again, dealing with harmonics is even in the telecommunication, those folks. So if you have a building that's extremely high in harmonics and you're not doing something about it, you're just sitting there and letting it go, you're not trying to mitigate it in some way or doing some of the things to determine it, then it also plays effect by putting certain types of interference on the actual communication system. And high frequency currents actually can be heard as buzzing or sounds or noises in a phone line, kind of like a loud pitch buzzing. And again, while not a safety concern on the telecommunication line, it does affect the performance of that line. And again, today we're looking for the optimum performance on telephone lines, communication lines, data system lines. And so this high frequency that's above the normal operating frequency can cause a problem. Well, not directly a safety concern. It is a concern that will likely cause electricians to be called back out and say, you know what, this harmonic, this frequency is causing a problem in our communication systems, and somehow you've got to figure out how to deal with it. And so, again, this high harmonic currents in the neutral conductor, again, is where you're probably going to see it. It's going to induce a high frequency current into the communication cable, and that's going to be something that people aren't going to want. Okay? So we want to talk about determining harmonic problems in a single-phase system. Okay, so we'll look at that, and of course then we'll look at a three-phase system. But how do we determine we have a problem? Well, there are several ways that we can kind of look at this problem and try to diagnose the problem. Obviously, there's equipment that we can put on to monitor and check it and to come up with what the fundamental harmonic is. But there's check all of your equipment, because equipment such as personal computers, printers, fluorescent luminaires with electronic ballasts can produce harmonics. They're very much known to do that. Any piece of equipment that draws current impulses can produce harmonics. So when we're dealing with, say, a single-phase system, maybe even if it's a single phase that's derived from a three-phase for like an office building, we want to look and see, what are we dealing with? What do we have? Well, we can look around and see that we have fluorescent electronic ballasts. Not so much the magnetics, but the electronic ballasts are ones that are going to create this harmonics. We're looking around to see, do we have a lot of personal computers? If it's an office building and everybody's got a computer at their desk and all that, those type of things, and we can kind of say, yep, that is current. We can review the maintenance records to see whether there have been any problems with circuit breakers tripping for no reason. Documentation. I'm a big believer that maintenance people should always document any incident so that it can be a running log. Now, people take that for granted, but I can tell you, in the first time that I talked to large companies and they putting together a program for maintenance, they'll say, what is one of the things you recommend? And I'm like, keeping a log of every issue that you have in the facility so that you have an ongoing kind of a legend of what's going on in the building. Do I have something that's constantly tripping? Is this breaker constantly tripping? Or we've had to replace this breaker multiple times? Has this motor been replaced multiple times? And not trying to rely on memory, but putting it down in a log. Because if things are just tripping or going off or burning up for no apparent reason on a repetitive basis, that can be a sign in a single-phase system that you've got some harmonic problems. Now, the other thing to look at is your transformers. So any of those applications where I have single-phase systems with a transformer, look for overheating. Okay, look and see whether or not the vents are obstructed. You have the clearance on the vents. If that's not the reason, look and see whether or not I have transformer history of them breaking down. Check transformers currents with an ammeter, capable of indicating. Obviously, you want to do true RMS current values. There's some that are true and some that are not. And you want to make sure that the voltage and current ratings of the transformer have not been exceeded. So you'll have a label that's on the side of the transformer. You want to take these readings. You make sure that all of your values are all in line, and that type of thing as well. Okay, that's just kind of some of the little tips to, and everything's in line, then you're probably okay. You're not having a harmonic issue. Now, meters. Let's talk a little bit about meters. Why you want a true RMS. Okay. Well, you want the true RMS because a normal meter that would be, let's say, average value, it uses a rectifier and it actually converts the AC into DC. So the values you're going to get, depending on your condition, are not going to be 100% accurate. So when you get a true RMS meter, they're going to cost a little more. But an average one, you're going to have to do a factor multiplier of 1.111 to change the average reading to the RMS value for the sine wave. And it can be a little misleading. So I always recommend get a true RMS. It costs you a little more, but the true RMS responsing meters calculate the heating effect of the current, and they are way more accurate. Okay, so the distorted waveforms, for example, in an average type of meter that does an average reading, can have an issue where the values are sometimes, for example, distorted waveform can actually cause the amperage value to be as much as 50% less than what the actual RMS value that you're taking a reading of. Greatly misleading when you see it based on a meter that's average and you think you're getting a certain value when the true RMS is going to actually give you the correct value. Okay, so you're not having to do any multiplication, you're not having to convert anything to true RMS, and you're getting an accurate reading. Okay, so invest in a true RMS, get rid of those average meters. Okay, if you're just taking some random voltage checks, fine, but if you're investing in yourself, you really want to make sure you do that. Another example is sometimes in a circuit, to kind of give you an idea, when we're making a check single-phase system, I can have a panel and I've got loads that are going out to computers. And I've clicked a true RMS meter versus an average RMS. You click it over the wire and you're doing an amp reading. It'll say average amp meter will be 24.8, right? And you click it with the true RMS and it'll be 36.8. Well, 36.8 ampere is the actual true reading, okay? Not an average meter indication of 24.8. So you get a better understanding of what current you're dealing with, okay? And to be honest with you, that is a neat way, if you ever want to, here's a little tip for you, a neat way to determine whether or not you have harmonics in a system from a low-cost perspective is to get you, whether you have in a single-phase system, is use two different meters. Get you a true RMS, and then get you one that's called average, just a regular one. It's not true RMS, and click both of them over the line, okay? And you click it over the conductors that are leaving from the panel that's going out to that circuit. Click them over it, and it's interesting because if you have a true RMS, it might say 36.8 amps, and then you have the average ammeter that'll indicate 24.8 amperes. Now, to determine the ratio of the two measurements by dividing the average value by the true RMS value. Okay, that becomes our ratio. So I take the 24.8 and divide it by the RMS, which is 36.8, and that gives me a ratio. And that ratio is 0.674, for example. So this is a technique that's using 2 meters. Now, I happen to have a true RMS meter, and amp probe or amp meter, and I have a regular, what's just an average. It's a non-RMS. And this is how I utilize these two when I'm testing a system on a branch circuit in a building to know whether or not I've got a harmonic condition. Now, just as a rule of thumb, that's how some of these power meters with harmonic displays work. For example, if I did this ratio, and it's just a rule of thumb, and it's 0.674. All right, now, a ratio of 1 would indicate no harmonic distortion. A ratio of 0.5 would indicate extreme harmonic distortion. Okay, so in my case, in my example, I had a 0.674. So 0.5 would indicate extreme harmonic distortion. So obviously I've got harmonic distortion. So when I'm doing this, I'm thinking, well, my neutral better be able to handle this situation because I've got this harmonic distortion, and it's going to play havoc on some of the equipment that might be on the system. But at least it tells me that I have harmonic distortion present in this condition in this building. Now, the downside to this method is this is what I call the pool boy method, is that it does not tell you the sequence, whether it's what harmonic factor. It doesn't tell you the name. So again, it's not going to. Sadly, it's not going to tell you what fundamental it's at. It's not going to tell you what frequency it's at. But you do have a good indicator that there's harmonics. Then and only then you would need to bring in a harmonics analyzer. And that's what I use to determine whether or not I need it. So if somebody paid me as an electrician to go to a building and they're having problems with transformers, they're having problems with breakers tripping for no reason, and all that, I might utilize the circuits that are tripping. I might clip the 2 amp probes over the line, or the branch circuit that's going out to it, and I'm going to look at a difference, and I'm going to do a ratio. And I see anything less than 1, I know that I've got harmonic distortion. Now, the closer I am to 0.5, I know that I've got a real serious issue. And for me, in our example, 0.6 was pretty darn close to 0.5. So I know that at that point, I can look at them and say, the reason that you're probably having issues is because there's high harmonics. What we need to do now is bring in a harmonic analyzer, and that will look at the harmonics. Okay, so all of this at least gives you a starting point, and it's a poor man's method of doing it until you need to bring in a more expensive piece of equipment in order to look at this harmonic distortion. And then you're going to have to look at what you're going to do, whether or not you're going to have to change circuits, increase neutrals, change transformers, what needs to be filtration, what needs to be done. Okay, so that's kind of the poor man's way that I do a single phase harmonic problem, or how I'm detecting problems under single phase systems. Okay, now what about 3-phase systems? How do I determine whether we have a problem with those? There's a little different, but how do I do that? Well, one of the things are given. It's the same pretty much. It's not going to be something you're learning new, okay? Everything that you just put into practice, it's basically be fundamentally the same way. Same type of problems harmonics exist. Because our harmonic problems in a 3-phase system generally occur because of a Y-connected 4-wire system. That's why we have those rules in the National Electrical Code about whether or not a neutral can be considered current carrying. And you notice that everything gets tied to a 4-wire 3-phase Y system, that we know that we typically have a delta connected primary and a Y connected secondary with a center tapped neutral. And when we have that, to test for harmonic distortion in a 3-phase 4-wire system, we measure all phase currents and the neutral current with both a true RMS indicating ammeter and an average indicating ammeter, just like we did. And we do this on the neutral, okay? We do this so we kind of come up with that concept. So we're at least setting the foundation of what we do, okay? Now don't get me wrong here. We're going to actually take these measurements from phase A, phase B, phase C, and the neutral. And this is what's neat about using just two basic meters to do this, a true RMS and then one that's just an average one. So if you've got an older one, don't throw it away. It's probably an average one, and then get yourself a true RMS, and you can use these before you even need to really get into some kind of fancy power meter with harmonic displays and things like that. Okay, so here's kind of the concept. So we're going to do each one. So let's start with assuming something. Let's assume that we have a three-phase system, and it's being supplied by a 200 kVA transformer and kilovolt ampere transformer, 200. And the current values are recorded. So we have phase A, phase B, phase C, or phase 1, 2, and 3, and the neutral. So let's kind of look at the values. So we clamped the amp probes, both of them, over phase A in our system. And the true RMS response was 365 amps. The average was 292. Then we clicked it over to phase 2, or phase B, if you will. And that was 396 for the true RMS. But it was 308 average for the average response meter, your typical clamp over ammeter. And then phase 3, we clipped them both over, and one was 387 for the true RMS, and then the average response for the ammeter for the average one was 316. Okay, so and then we did the same for the neutral, and the neutral was 488. Okay, now look at that. The neutral current was 488. And the neutral average response was 478 for the average meter. Okay, so those are the values that we wrote down. First things out of my mind when I'm looking at this is if I've got an average and a true RMS, I've got two different values. I can do the same ratio we just did, the average divided by the RMS. And what we're going to find out is I can look at this system and tell you that I've got a harmonic problem going on. Okay, because of the difference. There's going to be a value. Next, the first thing that I would look at is an astute person that's used to this would look at it and notice the amount of current that's traveling on the neutral. Okay, it's much higher than any phase current, which is why we have those issues with a 4-wire, 3-phase Y secondary, why that neutral has to be considered a current carrying conductor when we're dealing with this situation here. And in this case, we're dealing with something that's probably going to have the majority of harmonics issues because you're going to have a majority of nonlinear load application. All right, so this is kind of a cheap, poor man's way of doing it with 2 meters to kind of get a test. Okay, so if I were to look at the ratios, all right, so if you even do the ratio, we're looking at 0.7 and 0.8. Again, one being no harmonics, so we obviously have harmonics. And we obviously have neutral current that's exceeding the rating of the phase conductors. That tells us that something's going on. So this is the kind of thing where we take the readings and we have to assume this. And it's sometimes harder because engineers design it. And once it's already installed, and they go, crap, I've got issues with harmonics. And so I have to do something to try to solve this issue. Right now, we're trying to detect the issue. So how do we deal with harmonic problems? Now, once we've identified that we've got harmonic issues. Now, after it's been determined that harmonics are a problem, that we have them in a system, we can use this poor man's way of doing it, I like to say. And then at some point, we probably bring in a power meter with harmonic display, and it will get some more accurate readings. It'll probably tell us at this point, it'll reveal the name and the sequence of our harmonic condition, okay, distortion, so we know how to tackle it. Okay, now, but what if, once we determine we have an issue and exists, something must be done to deal with this problem, or it's just going to continue to be a problem for the electrical systems. Now, generally, it's not practical to remove the equipment causing the harmonic distortion. It's already in, it's already being run, it's already been budgeted, people have paid for it, labor's already done, it's already installed. What do? There are other methods that now you're going to have to kick in, and that's where the engineer has to come in and say, what can we do to try to offset this distortion problem? Okay. Now, it's a good idea to consult with a power quality expert because at this point they need to look at it and they'll look at the potential readout because at this point you've identified harmonic issue. Now you've gone to a power meter. It's a little more sophisticated. It's basically will start to break out the values so that you know what you're dealing with. Okay. And you need to know the nature of their harmonic distortion. So some general procedures when you're dealing with the harmonics is probably what the power quality expert is going to condition. And here's some things that they're going to do. Well, one of the things that they might try to do is look at all the circuits. And if they're dealing with a 3-phase 4-wire system, it's typically a 60 hertz system, and the neutral current is really just, when you start looking at it, what they're going to do is try to balance out all the phases, so that ultimately, if the phases are balanced out, then the neutral current is going to be 0. Easier said than done, but if you're looking at systems and you're looking at which circuit, by using the method I just showed you, you might be able to isolate it down to the circuit that's causing the problem, and you can tackle that one circuit. So that's part of what a power quality expert does, is that they'll go in, and when we identify a problem, they're going to actually spend time rooting it down and finding out where the problem is. What circuits are the problem? And then maybe it's something, if we're dealing with a 3-phase 4-wire system, then possibly they can reduce the issue of these harmonics by trying to balance out the current flow. And again, if it's 10 amps, 10 amps, 10 amps, and you have 0 on the neutral, obviously reducing that issue by getting that neutral to 0 is going to help your plight. Okay, that's one way. So that's one way of trying to reduce an issue. But more often than not, this is what you're generally going to do. And this is kind of neat, because a power quality expert will look at the specific issue kind of like an investigator, and they will break it down to wherever the problem is. And now they can implement something like a filter or harmonic filter. So if I'm dealing with what's more commonly dealing with is triplet harmonics, then what's going to happen is that's where you're going to, the neutral conductor is going to have a certain amount of current traveling on it that's in excess of its rating, causing a problem with it. So the harmonic filters can be added to the load. Now, these filters can help reduce the amount of harmonics in the actual line. These filters are constructed with a combination of things like inductors, capacitors, resistors. All of them are fine-tuned to a specific frequency for that harmonic. And they're designed to filter in a specific frequency of that harmonic in order to try to eliminate that frequency. And so you can have those put in place. There's series fine-tuned, there's second order or high-pass filters, there's third order filters. All of them are specifically designed in order to try to filter out that frequency. And if you get rid of the frequency, you get rid of the problem. So that is one way to do it, okay? One of the other ways to do this, again, is when you realize that you've got a problem, is that if you're going to have triplet harmonics and they're going to be affecting the neutral, then at that point, because that's where your big problem is generally, then some solution for people is, again, to oversize the neutral, okay? Another situation is that many times in a system, they might be sharing a neutral. Now, with changes in the code, every branch circuit has to have its own neutral unless they're a multi-wire branch circuit. But in applications in the past, one of the issues would have been a lot of shared neutrals, and of course that becomes a problem as well. So one way to alleviate that would be to run separate neutrals for each phase, okay? But nowadays, that one pretty much takes care of itself with the requirement in order to have separate neutral for each circuit. There is exceptions to that, again, multi-wire branch circuit, and there's an allowance for feeder applications. But just in the general rule, that one usually takes care of itself today. The next thing, again, would be simply to install a larger neutral. And since you're installing a larger neutral, it can handle more current because it's much bigger. So it is also impractical to supply a separate neutral conductor, like we just talked about, to each phase. It's pretty much not what's going to happen. So what do? You just increase the size of the actual neutral. So if you have A, B, and C and it has a neutral, then you just oversize the neutral. And some people call it a 200%, and different terminologies for it, but mainly we call it an oversized neutral. And that's to counteract the fact that the neutral current is going to be in excess of probably the phase value on that neutral conductor, and you're just compensating for it by oversizing the neutral, okay? Another way that engineers do this, and I don't like this way because I pay for something, I want to get something out of it. And what we're talking about is a lot of times the side effect of the harmonics is it's terrible for transformers. So some engineers will actually derate or reduce the amount of load that a transformer can handle. That's going to result in having multiple transformers because they're really going to, because of the elevated harmonics, that it causes the overheating, and because of that, what they're going to do is that extra current that's generated by that inefficiency of the harmonic distortion, they will break it out. Instead of one transformer, they will derate it so bad in order to handle the load. Now they will add 2 transformers or even 3 transformers, okay, to be able to handle this and divide the load amongst all these transformers in order to be able to handle it instead of one transformer. Not the ideal way to go. Again, you can get transformers again with filtration built into it. They're more expensive, or you can even get again harmonic filter systems in order to try to filter out those harmonics. Again, all of these are options to you to use, so there is choices in the system, and you have to make the choice. Okay, just remember that again, filtration or filter systems that are utilizing the filter system is designed with a mixture of inductors, capacitors, and resistors all combined together in this system, have to be installed on the circuit, and it can get quite costly, but if it's tearing up a lot of things, then that might be the way to go. All right. Now, another concept that we want to talk about is called transformer harmonic derating factors. You know, the most practical and straightforward method of actually coming up with a derating factor for a transformer that you know is going to have conditions of harmonics is a method that was done by the Computer and Business Equipment Manufacturers Association. Now, the method is kind of unique here. To use this method, you have 2 ampere measurements must be made. Okay, so you have to take 2 ampere measurements, one using a true RMS current of the phase, and the second is the instantaneous peak phase current. Now, the instantaneous peak current can be determined with an oscilloscope connected to the current probe, or most people use an amp meter today that are capable of indicating the peak value of current. Interesting enough, you might think this is funny, but there's a meter that's out there by, and don't laugh now, Harbor Freight, which is an amazingly well done by Ames. I think that they just brand it from somebody else, but this is an amazing meter. It has the ability to take peak current. It can get true RMS, all in about $120 range. And it's just, I've gotten rid of my Fluke. I keep that. That's my regular 9 RMS. And I also use that with my Ames. And I'm tell you what, it's an amazing meter. I've put it through the paces. Maybe I'll do a review on it, but it is an amazing meter and it's very affordable. I swear you could probably pay $400 and $500 for this meter for all the things that it does. It's just amazing. Anyway, I don't want to digress, but it can take instantaneous peak current values. It can actually also do true RMS, and you need these. Okay, so many digital clamp-on meters that have a capability of doing an average, true RMS, and peak values all in one meter, all the whole gamut in one. Okay, now, so let's do something here. So let's do an example. So this is what we're talking about, determining transformer harmonic derating factors. That is, again, recommended for when you're designing a transformers that might be subject to harmonic conditions. All right, so for an example, and then assume that peak current values are measured for a 200 kVA transformer. Okay, 200 kVA transformer. All right, now, these values, again, are added to the previous data obtained with the true RMS. So remember earlier we did our values, and we had the 365 for phase 1, the 396 for phase B, or 2, and phase 3 was 387, and then we had 480 on the neutral. Remember those we did? And then we did the average response, again, was the 292, 308, 316. So we had those two. Now we take the instantaneous peak current and add those to this table, and we get that from our meter. Our meter is going to give us our instantaneous values. So when we do this, we take all of these values and we do a formula. And the formula is pretty neat. It takes 1.414 and it multiplies that by the RMS phase current. Okay? So we take RMS phase current, and we'll do that in a second. And then you divide that over the instantaneous peak current. Okay. Now, this formula produces what's called a derated factor. And it's going to be somewhere between 0 and 1.0. Now, because instantaneous peak voltages of current is equal to the RMS, if you've ever asked what this means, it's RMS values times 1.414. I'm sure you've heard that before. That's how we get our instantaneous value. Okay, so but now just remember something now. The RMS value times 1.414, when you're trying to determine what the instantaneous is, that's a condition where you have no harmonic distortion. We've got a condition where we have harmonic distortion. So the values that we have in our phase 1, 2, and 3 in neutral that we previously did in our average is not going to be equal to our peak voltage, which is the RMS value times 1.414. That's when you have, that's simple. When we're doing instantaneous peak current, when you have no harmonic distortion. In our case, we have harmonic distortion. So we use the meter in order to come up with these values. And so our instantaneous peak for phase A, or phase 1, was 716. And phase 2 was 794. And phase 3, or phase C, whatever you want to call it, was 737. So what we have is for example, phase 1, it had a true RMS of 365. It had an average ammeter reading of 292. And it had an instantaneous peak of 716. Phase B had 396 RMS. And remember, all these are coming from a meter. Okay, I'm not just pulling these out of the air. This is based on those meters that I clamped on. Okay, so the phase B has a 308 for the average and a 794 for the instantaneous. That was a meter given reading. And of course, phase C was 387 for the RMS, 316 for the average, and instantaneous was 737. Okay, so, and then the neutrals were 488, 478, and of course, check this out. The neutral instantaneous peak current was 957 instantaneous. All right, now, those are values that come from a real reading. If I had there was no harmonics, perfectly 1.0, everything was perfect, then all I'd have to do was take the RMS value on your RMS meter and do it times 1.414, and that's going to tell me what my peak value is for my current. Okay, not going to be the issue when you're dealing with harmonics. Okay, you literally got to take the reading, and so we took the reading. So now, following the formula, which is the THDF, which is how we determine what our D rating is for our transformer. Remember, we had a 200 kVA transformer. So you take 1.414, multiply it by the RMS phase current, divided by the instantaneous peak current, and that's going to get you your THDF, which is your transformer harmonic D rate factor. Now, how do we do this? Because we have 3 phases. We don't want to do this for each phase. It's not necessary. So in our case, we take the phase, so we start the math with our RMS. We take 365, and we do 365, and then we take phase B at 396, plus phase C, which is 387, and we divide that by 3 so we can get our average. And in our case, that was 382.7 amps. So that's our phase RMS average. Now, we then have to do our peak, because we need to get our instantaneous peak current, and that was 716 plus 794 plus 737, right? So we have those, and then we divide that by 3, and that's going to give us our peak average of 749. Now, those are the values that we plug in. So then we use the formula, and we go 1.414 times 382.7. Remember, that was our phase RMS, phase current. And then we divide that over our peak phase, which was 749. That's going to give us a 0.722. Now, what did we say earlier? We take our 200 kVA and we multiply it by our ratio, and that is our new ratio. So we do that. So it's a 200 kVA transformer. It would be derated to 144.7. What is that? 200 kVA times 0.722. So it's 144.4 kVA. So because of our issues with our harmonic derating, and it has to take place, we have a 200 kVA transformer, and many engineers will now reduce it or derate that transformer to a capacity of 144 kVA rather than the 200 kVA. And that's kind of what engineers do to offset it. Now, you can get a much more expensive transformer with the filtering in it, and you might be able to get more of that 200 kVA out of it, but it's going to be a lot more expensive. So many engineers will use this transformer harmonic derating factor in order to derate a transformer in order to be able to not overload a transformer based on all of the harmonics that are going to take place. And this is how you do it. So this is just a method of how to use a formula with a amprobes, or ammeters, I should say, that measures true RMS. Then you have another one that does average response ammeter. And then, of course, if you have one that also has instantaneous peak value, there you go. Now, you might have a meter that does all three of these. So you just make these readings down off of phase A, phase B, phase C, and then you can apply this THDF formula, and that's how you can do what's called transformer harmonic derating factor. And that is probably the most common thing that engineers do, and that is based on what's called a Computer and Business Equipment Manufacturers Association model or method in order to be able to do that. So hopefully you got something out of that episode today where we talked a little bit about transformers and some of the things that you can do with harmonics and how you can alleviate it. And if you're ever lucky and you have a system that does not have harmonic distortion, then you're good to go. But if you're dealing with a system, whereas you're a single-phase system that's being derived from a three-phase system full wire, or you have a full wire three-phase system that's a Y secondary from a delta primary, and you have elevated harmonics, it can play effect. Don't just think that it's the secondary. It's going to play havoc on the primary side for that delta winding as well, folks. So just think about those things. So it's important to have a plan of attack for dealing with harmonics. Okay? Again, this is about a 30,000 foot view of it. I tried not to go too deep. I gave you some practical ways to use meters for it. Again, I use multiple meters, even though my meter will do both the RMS and the average response, as well as it will do instantaneous. But I still like to use the two different meters. For my Ames meter, I'm able to get the true RMS and the peak, and then I clip on my Fluke, which is an older model, that I will get the average, and that's how I do that if I'm going to go in and analyze a system. I don't do the steps beyond that where I have harmonic meters that actually go into the real deep analysis, because at that point, to me, it's unless you're trying to document it for some reason, it's a moot point. Once I become very confident that my system has harmonics, and depending on whether or not the values are 0.5, 0.6, or 0.7, then usually I'm going to then start defining which circuit is generating these harmonics, and then I'm going to tackle it from that perspective. And then we're going to look at the cost, whether or not it might be just as easy dealing with the neutral. Are the loads that are on it, like luminaires, electronic ballasts, computers, which aren't really going to have a problem with the computers. It's not like a motor. It's not like a transformer issue. But can I tackle the issue from a neutral conductor aspect of it, oversizing the neutral, or maybe I might recommend filtration at some point in the system at an isolated point. Transformer replacements are pretty difficult. Chances are if they're having transformer issues, did they calculate the transformer using the demand factor ratios, or did they try to get every bit of capacity out of that transformer and now they've got a problem? Do they have to replace the transformer, go to a bigger transformer? Do they have to separate the loads down into multiple transformers in order to reduce the capacity on a transformer because it's burning up because of this harmonic issues? You have to look at it from a case-by-case basis. But I just wanted to give you an overview a little bit of harmonics. This is by no means a definitive. I am no means an expert on all things harmonics, but it's just kind of giving you an overview of some of the things that you might be able to do in order to reduce your issues with harmonics. Till next time, folks, stay safe. God bless. And hopefully you visit our website at masterthenec.com and look at the courses we offer. Also listen to our podcasts on our website as well as on our YouTube channel at youtube.com/masterthenec. Hopefully you check out our merchandise. If you're an electrician, you want to get some of the swag, go to electricianpride.com. We appreciate you. Thank you for listening. Until next time, stay safe. and God bless. You've been listening to Electrician Live with your host, Paul Abernathy.